Hi again, this is part 2 to the notes for 8.1 and 8.2. We have 2 more problems to work through in this section. The first one gives us sigma. If you read through, we're given that sigma for the first population is assumed to be 19 and sigma for the second population is $24. And the samples are independent, normally distributed. Since it's normal distribution, the size of n doesn't matter, and our ho and ha is based on the prompt. So a travel agent claims that the average daily cost of meals and lodging in Texas is less than in Virginia. Texas is population 1, and it's less than population 2. So then our ha is the claim, and our ho will be the complement, so greater than or equal to. The table to the left shows the results of a random survey of vacationers. They're independent, and we are going to use z since sigma is known. So you find z just like we've done in all the other examples by subtracting the 2 means. You're going to subtract the 2 population means, which since we're assuming they're the same will be 0. The square root is a little nasty. 19 squared over 25. 20 squared over 20, sorry, I need to go back to bed. 19 squared is correct, but I should have put 24 squared over 20. And I need to calculate this z, so find your calculator and crunch the numbers, and let's check and see if we match. So I get negative 0.9124. How do I test this? Well, remember your p-value statement is going to go in the same direction as your ha. So we're going to do the probability that z is less than this value. We can do this with technology by using StatCrunch. We can also use our table for this one and look at negative 0.91. I am cheating this one and I'm using my calculator in case you can hear the clicking. But either way, you should get something close to 1808. This is a very large probability when you're considering a statistical move, and so since this p-value is greater than the alpha level, we fail to reject the null. In order to make a conclusion about the problem, however, we need to go back and look at the prompt. So if we fail to reject the null, you've seen me do this before, I'm going to say, okay, let's keep this one. Dang it. Let's keep this one, which means we'd have to throw away this one. So when we say, is there enough evidence to support the claim, if you look at it like this, since you labeled the claim and you chunked it, then the answer is no, there's not enough evidence to support the claim. We're still going to look at that one is bigger or equal to than the other. Now, I know that this looks confusing, but if you look here, the state of Texas and the state of Virginia, it looks cheaper, right, in Texas, but the standard deviation's bigger in Virginia. So when we run the probability of this happening, it is not small enough to throw away the fact that this is the actual truth. Now, we'll never know the honest truth of the population unless we did another statistical study. And we probably don't really care at this point. I don't know about you, but I'm doing hypothesis tests in my sleep now. I've had enough. Let's do something else, right? Okay, this last one, the numbers are gross, so bear with me. The problem is that the variances are equal in this problem, so I have a different way of calculating the denominator for t. How do I know I need t before I even get started on this problem? I see that n's are small, and I see that sigma is unknown. So the only thing that would keep me from using t is if I didn't know that the populations were normally distributed. So we are going to use t. Our calculation is going to be different than in the last video because the population variances are equal. So let's try to get started here. Manufacturer claims that the calling range is greater than that of its competitor. And then we perform this study to see if we can support the claim. So the claim doesn't say equal to, the claim says his is greater than the competitor. So we're calling him 1 and the competitor 2. Then the hoe would be the opposite direction. And we need to find t. T is calculated by subtracting the sample means and then subtracting the population means. Why is this always 0? Because we are assuming that mu1 equals mu2. Alright, now the dividing piece, I have to go back and look at my formula sheet. So don't watch, so I don't make you dizzy. But I scroll way back up here, and it says if the variances are equal, I need to do the following. This is so gross. Ugh. Okay, hang on, I'm going to cut and paste that back to our problem. Okay, so I have some serious nasty work to do. I have to calculate, this is read sigma hat. I need to calculate sigma hat by plugging in all that nonsense. So let's see if I can write small enough. So my sigma hat would be the square root of n1 minus 1, so that's 13, times s1 squared, that's 45 squared, and then plus n2 minus 1, so that's 15, times s2 squared, which is 30 squared, all divided by 14 plus 16 minus 2. So let's get that number first. So I got approximately 37.7137. Now that goes here, okay? So then this would be equal to the 37.7137 times the square root of 1 over 14 plus 1 over 16. So we need to multiply that. Gross Ola. This is now worth 13.80179. That's my denominator. How disgusting. Thankfully, this scenario does not come up very often. You see it once, maybe twice in the homework, I think. So your numerator is 25. I'm going to divide by the denominator. You get 1.81136. Now the other thing to note is the degrees of freedom are calculated differently for this type of test. So we're supposed to add the two samples together, which is 30, and subtract 2. So the degrees of freedom is 28. So when we go to run this test, the p-value would be the probability that t would be greater than this value with degrees of freedom of 28. You need your technology to work this problem. You can go into StatCrunch. In StatCrunch, you'd go to Stats, you'd go to Calculate, and you would pick the T calculator, and then you could tell it the degrees of freedom and that you want greater than blah. Okay, so using my technology, I get this value. If you use the table, you cannot get an accurate answer. You can just get between two numbers. But the alpha level is set at 0.5. So what does that mean this time? That we actually reject our null because the p-value is less than the alpha level? Rejecting the null does what for us in our problem? So come back to where you wrote your statements. If I reject the null, it means I'm throwing this one away, and I'm keeping this one. Notice I'm not saying it's true, I'm just keeping him. I did not write which one was the claim, so boo on me, I have to go and reread the problem. Nah, get over yourself, May. So the manufacturer claims that his calling range is longer than the leading competitor. So the claim was that it was longer. And so do I have evidence to support the claim? In this case, yes, we do. Woohoo! Good luck with 8.1 and 8.2. And 8.3, we will look at having dependent samples. So the technique will be different in 8.3, and we will rely very heavily on using StatCrunch to help us do our number crunching. So stay tuned. It'll be loads of fun. Can't wait.